Okay, so welcome everyone. My name is Staals, and I'll talk to you about kinetic geodesic Voronoi diagrams in a simple polygon. Alright, so before I explain what that actually is, let us actually look at why you might want to care about it. Yeah, so suppose that you have some sort of a path planning problem in which you're given a simple polygon P that somehow models the environment, and you are at position Q, this red point over here, and somehow you want to reach point S. Right, and so think as point S as some sort of a server or a person or a robot or a place that you want to go to, right? Something that provides you with some service. Okay, and then, clearly you cannot walk through walls, and so that means that you have to somehow find the path that stays within the polygon, and, preferably you would want a short path, right? But now imagine that if this point S, this site or thing that you want to reach is actually a person or a robot or something like this, then this point might be moving as well. Yeah, and actually maybe especially if it's a robot or so, then there might actually be many of those sites or robots at which to which you can go. And clearly, again, you want to get to the closest one. Yeah, and so, here, clearly this guy S is not really the one that you want to go to. Instead, you want to go to this P guy because it's much closer. Yeah. But, okay, so if you were somewhere over there, then maybe now it's suddenly a lot less clear who is actually the closest site. Yeah, and, how would you figure that out? Now, suppose that our blue points are our set of sites, that they're actually static, right? So forget that they're moving for a while. Then you could solve this problem by building a geodesic Voronoi diagram, right? So a Voronoi diagram is somehow a partition of the space, in this case some sort of a polygon, into regions, one region for every site, such that if you're in this region, so in particular if you're into this blue region, then P is somehow the site that is closest. Right, so and if you're anywhere in this blue region, just go to S rather than go to P rather than to any other blue point. Okay. Now, admittedly, like this Voronoi diagram, this purple thing that I've drawn here, admittedly, this is not exactly what the Voronoi diagram of this simple polygon will look like, and we will see a better or more detailed view of what it really looks like a bit later. But for now, right, so somehow there's this purple diagram, this purple somehow graph that splits the polygon into these disjoint regions. That's the important part. Right, and so, okay, so now if our sites are moving, then it also means that this Voronoi diagram, right, so this purple subdivision is somehow changing. Right, in particular over here, right, so our point P is somehow moving upwards, and this our previous point S is somehow moving downwards. And as a result, that sort of means that this horizontal or more or less horizontal blue part of the Voronoi diagram, the bisector between P and S, is somehow also moving, right? In this case, it's moving upwards. Right, and as you'll see, that will mean that that at some point then somehow the Voronoi diagram will change. Right, so here now this vertex U in purple is somehow above vertex V, right? But, as these sites are moving, then at some point you'll see that they'll flip around and they change, right? And this somehow changes the structure of the diagram. And, basically the question is then, okay, so when does that happen, right? So when do these changes occur? How often do they occur? So even if we know that, then somehow can we use it to sort of maintain this Voronoi diagram, maintain this structure? Yeah. Okay, so, maybe one additional reason, so why would you care about this? Well, so here we solve these sort of nearest neighbor queries, right? So given some arbitrary point in the polygon, find whoever is closest. But actually it turns out that for many problems that just involve points that are moving the polygon, let's say maintaining some sort of minimum spanning tree or maintaining a nearest neighbor graph or some sort of spanner, in many of these cases it's very useful to have this Voronoi diagram, and then using it you can argue that you can maintain these structures or compute these structures. Yep. Okay, so well, then maybe in a bit more detail, so what does this diagram, what does it really look like? And actually, it's known that the geodesic Voronoi diagram in a simple polygon can have linear complexity. Linear not only in the number of sites, so the number n of blue points that I have, but also linear in the complexity of our polygon, here, m. In particular, there will be these vertices of the Voronoi diagram, in this case like this, these pink vertices, like vertex v over there, that somehow really depend on the complexity of the polygon. And you'll see that sort of if you stand just below this vertex v, then the shortest path towards S, it will somehow have to bend at this vertex w and then go towards S. But if you're just above this vertex v, or above the red segment in general, then you can sort of, well, you don't have to visit this polygon vertex w. Yeah? And so these pink vertices, they somehow, I mean, they add to the complexity of the diagram. And moreover, so as our blue sites, our blue points, if they are moving, then actually the locations of these degree 2 vertices, these pink vertices, they also move, and they can also change and thus interact with the other sort of the purple vertices of the diagram that we saw before. Yeah, and actually even so, they can even interact amongst each other, right? So here, if our blue site in the bottom right, so somehow if it keeps moving to the bottom right, then you'll see that this red line segment, it will sort of rotate in counterclockwise orientation, causing these vertices u and v to sort of bump into each other. Yeah. And this also adds like different vertices and different types of events and somehow complicating things. Okay, so well, one other thing, so when we say that we want to somehow maintain the diagram efficiently, then, well, what does that mean exactly? What we'll do is we'll use the kinetic data structures framework, which basically tells us that there's, well, 3 things that you might want to care about. One is what's called compactness, which says essentially, okay, so how much space does my data structure use, or use at most? The responsiveness, so, well, we saw that there will be these times or events when the structure of the Voronoi diagram changes, and then I have to do something, right? I have to update my data structure and fix things. And so how much time you need to fix each event, that's called that measures somehow the responsiveness of your structure. And finally, there's this notion of efficiency. So, so clearly there's these times at which sort of the output of the structure, right, the structure of the Voronoi diagram changes. And so, well, I mean, at these times, the data structure certainly has to do something. But the structure itself might store additional information that has to change more often, right? And so basically what you might want to care about is the number of times that the data structure has to update itself. So this is this number of events processed over like the minimum number of times that the data structure has to do something, right? The times at which the output changes, and certainly the data structure has to update. Okay, so then what are our results? Well, so let's start easy, and let's start with only having 2 sites, P and Q, that somehow move linearly. And then we care about somehow maintaining, well, their Voronoi diagram, which is just a single bisector of P and Q. And then it's known that this bisector can have linear sides, right? So this is this story with like these very many degree 2 vertices somehow. And then what we show is that this bisector can change at most a cubic number of times in the complexity of the polygon, right? So even if P and Q change linearly. And so this is a very high bound, of course, right? That cubic sounds like a lot. But what we can actually show is that this bound is tight. So we have a construction that shows that even if P and Q just move along lines, then a single bisector can already change a cubic number of times, which I guess is sort of surprising. Okay, so, well, then we present a kinetic data structure to maintain this bisector, and so it has linear size. It processes these only m cubed events in log m time per event. Right, so in terms of our measures, our data structure is compact. It is efficient because somehow this ratio of the number of times that a data structure does something over the number of times it may have to do something is constant. and it's also responsive in a sense because it uses only logarithmically time per event. Right, and apart from these things, our data structure actually also supports updating the movement of one of our points. Right, so we can say that suddenly P now moves in some completely other direction. And we can again do that in log n time. Okay, so then next ingredient is somehow a Voronoi center. So if I give you 3 points, let's say P, Q, and S, then there's this Voronoi center defined by these 3 points, this point C, that is somehow equidistant to these 3 points. Right, so these, in particular, like these red shortest paths, they all have equal length. And so as P, Q, and S move, they basically define movement of this point C, right? So as P, Q, and S move, this point C also moves. And so what we can again show is that as P, Q, and S move linearly, somehow this trajectory of this purple point, this Voronoi center, again has at most cubic complexity. And again, this bound is tight, right? So again, some matching Lowerbound construction. Okay, then we also have a kinetic data structure for this that uses linear size that processes these m³ events, this time in log squared n time per event. Right, then again we can update efficiently. Right, and so again in terms of the results, this is like it's a compact data structure. I mean, you cannot really hope to use less than linear space. It's efficient because we're only processing these m³ events, nothing more. And again, it's still responsive, right? So polylogarithmic is still very fast. Okay, so then using these results, we get our results for the Voronoi diagram itself, right? Which has linear complexity now in both the number of sites and the complexity of the polygon. But here we do have sort of worse bounds. So we argue that the number of changes of the geodesic Voronoi diagram is at most something like n³ times m³, which is kind of fairly high, I guess. And we only have a lower bound that says that the number of events is at least n, the number of sites times m³ plus n squared m. Right, so there is quite a gap between the upper and lower bounds here. Sort of in our defense, like even if there was no polygon, but I just have n sites that are somehow moving in the plane, each at different speeds, then the best known upper bound for this is still n³, right? So cubic in the number of sites. So admittedly, this is kind of a hard problem, I guess. Yeah, and then okay, so based on these results, then we also get a kinetic data structure for maintaining the entire diagram. It has linear size. Well, we're processing these m³ events, this time in k log squared n time per event, where k is the maximum number of neighbors that a point has. Right? So if I have some sort of blue point, then k is the number of neighbors, neighboring Voronoi cells of this site. And again, ideally we would get rid of this k, but again, that seems pretty tricky. So in the remaining time, let me tell you about 2 things. Like one is I want to give you some idea of this m³ lower bound for a single bisector, and I want to give you some hints on why maintaining this kinetic data structure is kind of complicated. Yeah. So as for the lower bound, so the idea is going to be as follows. We're going to build a polygon like the one that you see over here, and we're placing P in this pocket in the bottom left somehow. Yeah, and in the top left there's this chain C of P with vertices. And so now imagine that you're actually at this point R, and you're walking downwards. Yeah, then what you see is that every time that you're crossing one of these gray lines, and so a gray line is somehow an extension of one of these edges in our chain CP, then the shortest path from our point R to this point P changes. Right, so in particular, if we're somehow crossing this line, then now our shortest path suddenly has to bend at vertex V and to get to P. Yeah, so somehow similar to what we saw before. Okay, now what we do the same thing for Q, right? So we place Q in this pocket in the bottom right, and we build this chain C of Q, right? Which again gives you this sort of fan of gray lines coming out of this this chain C of Q. Yeah. Okay, and okay, so this basically this gives us this sort of grid structure of these gray lines, and well, ideally what we would do is we would flatten this these chains CP and CQ such that actually this entire grid structure of gray lines somehow it appears very small in this very tiny region R, and like I said, we can do this by scaling these chains appropriately. Yeah, but for drawing convenience, if I were to do that, then you wouldn't really see anything. But imagine that this entire grid structure is in this tiny region R in the middle somewhere over there. Yeah. Okay, so then what happens with the bisector of these points P and Q? Well, it's some sort of Y monotone curve that somehow crosses this grid. And like we saw before, right? So every time that somehow that this bisector that it intersects one of these gray lines, so either the shortest path towards P or towards Q changes, right? So actually, any such crossing actually corresponds with one of these pink degree 2 vertices that we saw before. Huh? So now let's make P actually move to the left. Then what's sort of happening is that if you're sort of standing on this gray grid somewhere at the top, then P is coming closer. Yeah, and so that means that P is somehow actually pushing the bisector towards the right. Right, so it's doing that. And okay, so then, basically every time that the bisector, once it sweeps over one of these gray intersection points of two of the lines, then actually the structure of the bisector changes. Right, so if I had somehow two vertices, U and V, and U is above V, then, well, I mean, once you sweep over this intersection point, then these two vertices, they somehow flip. Yeah, and so even this very simple scenario where Q is fixed and P is just moving, and only P is moving somehow, this already gives you m squared events, right? We're sweeping over all m squared intersection points. Okay, so to get m cubed, what we're going to do is we're going to make this bisector sort of sweep back and forth over this grid a linear number of times. Yeah, and thus giving m cubed events in total. How do we do that? Well, essentially we also make Q move, and we add these two convex chains, dp and dq at the bottom, and sort of the main idea is that sort of in the default state, think of it, so if the shortest path from P towards the top and the shortest path from Q towards the top, and they have sort of fixed structure, then P is sort of very slowly pushing this bisector to the right. Yeah? But sort of imagine now that the first thing that will happen is somehow that the shortest path of Q will change. So in particular, Q, like the first vertex, it will lose its first vertex V. Right, what that means is somehow that now the shortest path from Q towards the top, it doesn't have to bend at V anymore, and somehow Q becomes cheaper, right? Relative to P, Q suddenly becomes cheaper. And as a result, this will mean that Q will now start pushing the bisector to the left, right? And so Q moves it backwards. And it continues doing so until P, the shortest path from P to the top, now changes combinatorially. Right? In particular, it will lose its first vertex U. It doesn't have to bend there anymore. And this means that somehow now P becomes cheaper or decreases more quickly again towards this distance towards the top. Yeah, and this alternates a linear number of times, and thus we get a linear number of times that this bisector sweeps back and forth, changes direction. Okay, so so what about this kinetic data structure then? Well, okay, so let's again start easy with just having 2 points P and Q. Then there are all of these different types of events that we somehow have, and so like for example here, the first thing that will happen is that these two pink vertices in the top of the bisector, they will sort of hit each other, and well, in this case one of them disappears. And then, well, as we move, so here now the bottom pink vertex, it somehow hits a wall or a corner of the polygon, and then we have to change that. But actually, so while at the moment when this happens, then sort of this purple vertex at the bottom also has an event, and it suddenly sort of jumps to this other edge. Right, so one part that makes life complicated is that some of these events may happen simultaneously, and somehow we have to do all of this bookkeeping correctly. Okay, so then actually, so if we sort of go back at the time when this polygon vertex V is equidistant to P and Q, then it turns out that this entire pink region becomes part of the bisector. So for any point in this region, like the shortest path to P and the shortest path to Q, they share, well, they both go to V and then to P and Q, so all of these points are equidistant to P and Q. And now life gets complicated when there might be these blue points, other sites, they are somehow in this purple region, right? Which would mean that actually our entire Voronoi diagram, there might be this entire region at the bottom somehow that has all of these pieces of bisector and a Voronoi diagram. And actually all of those pieces, right, they somehow, the complexity of these pieces, it involves the number of polygon vertices n, and so we have to be able to very quickly, all of these things depend now on P, but they have to switch to depending on Q. Right, so more specifically, let's look at actually one of those sites, S, and sort of there's this piece of bisector between P and S, right, which again might be very complicated itself. And so certainly at this time, this piece of bisector actually has to switch to being a bisector of Q and S. Yeah. So how do we do this? Well, essentially our data structure that stores this piece of bisector will make sure that it doesn't actually store things to P itself, but to this vertex V somehow, and only this, and somehow store this piece from V to P separately, right? Which intuitively it sort of quickly allows us to reuse the existing data structure to become to use it as the bisector of Q and S instead. Okay, so final part is sort of similar to this, in that if I have these sites that are moving, and here I have this complicated bisector between P and Q, but as S is moving, it suddenly becomes there's this vertex V that is becoming equidistant to P and S. Right, and here we again see that somehow now there's this purple region that is again sort of part of the bisector, right? It's equidistant to P and Q, and essentially what this causes is that our very long, complicated bisector between P and Q, we have to split it, right? And part of it is still the bisector between P and Q, but part of it, like this top part, has become the bisector of S and Q, right? And that we have to somehow deal with this splitting aspect. And so basically, like most of the complexity is in our KDS for like this single bisector, right? It should support these sort of updates and splits, and once we have that, then we can sort of use it to get the KDS of the entire Voronoi diagram. Okay, so then, what do we do for future work? Well, right, so I guess the most important part is this upper bound on the number of events. So we currently have this n cubed, m cubed bound, which we believe is an overestimate. So we're expecting that the true answer is closer to this lower bound that we have. But how would we prove this? I guess that's open. The other thing is, okay, so can we somehow get rid of this k factor in the update time, which is somehow dealing with this scenario that somehow many sites simultaneously change whom they have an event with, and so we partially solved this by somehow storing things with respect to Polygon vertices, but life is more complicated than that. Okay, so what happens when our sites would be moving not just linearly, but using some more general movement? Usually you can somehow deal with this. And finally, I guess, so what happens when our polygon has holes? And there we really don't know anything. And that was it. So thank you for listening.